Okay, I guess that you
The
should
next
see my
speaker, yes, now we see it.
screen.
The next speaker is Robert Fickler from Slovak Academy of Sciences from Slovakia.
Hello, everyone. Yes, my name is Robert Fickler, but I'm not from Slovakia, but Finland, Tampere University. So, but
it's sorry, my mistake.
No problem at all. I was anyway on holiday and just came back, and then very late I got this still the opportunity to join. So thanks very much to the organizers for giving me the opportunity, and congratulations to them as well to put in these very difficult under these very difficult circumstances to put together such a really nice program. So I enjoyed it a lot over the whenever I found time yesterday and already today. So thank you very much. Yeah, today I want to talk about quantum photonics, experimental quantum photonics, I should say, using structured photons. And later on, I hope I will show you a few experiments that we did here at Tampere, and I hope this then gets a bit more clear what I mean by this title. But maybe first, Tampere is in Finland. I guess all of you know where Finland is. It's pretty much in the north, a bit more north of Ukraine, a bit more west, I would say, or maybe no, actually it's just north. And Tampere is in the south of the north. And it's, if you haven't been here, it's an old industrial or older industrial city. I would say it has its own atmosphere. I enjoy it quite a lot. We have like sometimes even northern lights, and since it's the sauna capital of Finland and therefore maybe the world, we can go swimming all year round. So yeah, I enjoy it. Although I'm not Finnish, I really enjoy this culture here. The university is a bit outside of the city. It's also a nice campus. So where we do different research in terms of physics, we are very strong, I would say, in terms of photonics. So maybe you haven't heard about Tampere University in the context of quantum, but I guess in photonics, it's a really strong research hub. And I just listed here all the groups that are working on photonics at Tampere University. And actually recently, maybe the last 5 years and 3 years where the theoretical optics group and my group started here, it also, we like university moved into quantum optics and quantum photonics. So yeah, I hope with also the presentation today that you then have an idea what's going on here in Tampere. Okay, so my group is called Experimental Quantum Optics. And we essentially, if you want to structure the group's research work, we essentially work on 3 topics. So one where we always collaborate with others essentially is where we investigate light-matter interaction on a single photon level, on a quantum level. So we have plasmonic structures or different nonlinear material where we want to, or where we investigate quantum effects, or for example, the generation of single or photon pairs. So this is together with groups from Aalto University and Espoo near Helsinki, or another nonlinear optics group at the university here in Tampere. And then we also do some classical optics. And there it's usually often ideas come up that we want to transport to the quantum domain, but very often in the classical domain, they're also very interesting or even and very often easier to do. So we investigate the structures of light and try to make it more and more complex. So just 2 examples that we did recently. So you can have a light field where the intensity, if you see it propagate, it spirals around the optical axis over a certain distance. So it's a relatively simple interference effect, but you can have light fields that do this essentially while propagating, which I think is pretty neat. And we showed that, other people showed that earlier, but we used it then to measure distance or down to 2 microns even by just following the spiraling essentially. Another recent experiment we did was to make the light field more complex and connect 2 different degrees of freedom, meaning in this sense polarization and the spectral domain. So we had what we call spectral vector beams. So every single frequency component of a laser pulse had a different polarization. And we showed that you can use this to do spectroscopy measurements very, very fast. Relatively simple by just playing around by making the light field essentially more complex and not your measurement scheme in the end. But then all of this, we also try to push towards the quantum domain, and the biggest part of the group is essentially working on quantum photonics, and there towards, very often we use the high-dimensional aspect of structured light. And I will come to that in the next slide. And if you listened to the talk yesterday by Mehul and Malik, they are also working on similar experiments. So we try to use this high dimensionality, not just qubits, but more complex quantum states, and we use structures of photons to realize it in the lab. And today I want to talk about these three essentially experiments, 3, 4, depending on count. And yeah, I will explain it then in a bit more detail later. So I already mentioned quite many times the structured photons. So what do I do? What do I mean by that? Is that you can decompose any light field in a certain basis. Yesterday we heard from Neil the pixel basis, which of course fits nicely to cameras. But essentially a very well-known basis as well is these Laguerre-Gauss bases, where there's two indices, so two characteristic numbers, if you want, or quantum numbers. One is the azimuthal one, and that's very popular. So it describes how many phase ramps essentially do you see or do you have in your light field when you go around the optical axis. So the light field is in that sense, the wavefront is twisted. That's why it's often called twisted light. And it's connected to an orbital angular momentum of light. So that's why they have become very popular over the last 30 years. But there's also the second quantum number, second kind of degree of freedom, because the transverse plane of light of a light field is essentially a 2D. So in here it's the radial degree of freedom. So you see, you can also have more complex light fields and have additional rings on it. I should say that the brightness, what you see here, depicts the intensity, and the color code is essentially the phase of the light field. So here you see you have this azimuthal phase ramp, and here you have multiple rings that are out of phase. These modes are stable upon propagation. So when you have a light field like this, it propagates like this, it just diverges like any Gaussian light field. And for completeness, I just showed, like this is mathematically, these are the solutions in cylindrical coordinates to the paraxial wave equation that describes such light fields. And if you do it in Cartesian coordinates or in elliptical coordinates, you get other mode families, and they're equally valid. For us, we use them, the Laguerre-Gauss mode family, quite often because they fit quite nicely to our cylindrical symmetry of our lenses and so on. And as I said, why do we use them in the quantum domain? So all of them are orthogonal. They form a basis set, so we can use them to encode quantum information. And as you see here, there's multiple of these modes. So we not just can use them to encode qubits, like this would be our 0 and this would be our 1, but we have multiples. So we have a 0, 1, 2, 3, 4, 5, and so on. So we encode high-dimensional quantum states, qubits, where D labels should depict or label essentially the D-dimensional state that we have. So, and it's not just us, there's multiple groups working on that. So why, and this is our very short overview, strongly biased, of course, what people do with the spatial structures in the classics domain. I mean, right from the beginning with the orbital angular momentum, these modes have been used to rotate particles and twisters and tweezers, sorry, and maybe you've seen them already in stat microscopy, but you need this donut shape as well. And then recently also people, like recently means 10, 15 years, people use them to encode more information even in classical optical communication schemes. And then in the quantum, of course, you look into the foundations of quantum physics. You can use them to test inequalities. We've heard yesterday from Neil a little bit about that. And you can also do it for simple computations. I will show you later one example, or simulation, people working on that, and also communication. And in the earlier talk, we heard that they are used over a few kilometers, and I've been involved in such experiments. I agree, they are for really long distances, they're getting pretty challenging because you have this, I would say, nice donut shape, but of course it makes it hard to detect if you have nothing, no intensity in the center. But still people work on that in the quantum communication scheme, also through fibers. So these structures are pretty nice because they give you so many opportunities to research on. And as I said earlier, or today, I want to focus essentially on two parts, separated. The first one is shorter, the second one will be a bit longer. I hope I stay in time, or I will do my best. So the first one is we use these twisted photons or structured photons to realize a quantum finite automaton. So if you're not haven't heard about it, speaker from yesterday, Abu essentially, I think he spoke about the Q world, but he was a collaborator with us on this project, introduced us to this concept, and we were able to do then an experiment even in this direction. So a finite automaton is a very fundamental computational device that just reads strings and then makes a binary decision. So the simplest thing would be a machine that says this password is valid or not. So you type in a certain length of string and you get the answer yes or no. And one very specific problem that we then investigated also with quantum finite automaton is, is the length of a string of a certain, like, is the length of the string a certain prime number? I will get back to that in a second, why prime number. So let's say you have a string of length, of certain lengths, then you put it in. A classical finite automaton would have is in a certain state, then you read essentially the string, you hop on to the next state, you read the string, you hop on to the next string, you hop on to the next state, and so on. And if you have the right automaton, let's say you want to check prime number 5, and you have 5 states, then you always end up in the beginning state, which is also the accepting state. So your automaton works for 5. And why prime number? Because for this specific problem, it's known that classical finite automaton require exactly the prime number of states to recognize such a prime number, it's called such a prime number language, essentially. So what are now quantum finite automaton? Essentially very similar, but you have a quantum state, and when you read a string, you perform a quantum operation, meaning a unitary operation on it, and in the end, you project on your accepting state. And why is this advantageous? And it's known that for this problem with the prime numbers or detecting mod key languages, quantum quantities are exponentially more efficient in terms of resources. There's some sound going on here. I don't know. Yeah, so let me get back to that. So for quantum finite automaton, it's known that it's efficient in terms of memory, or it's more memory efficient in terms of states that you need. So you need less states. Classically, you always need the prime number p states. Quantum mechanically, you need less. Example would be if you have just a qubit and you want to test the language mod 5, you perform 5 unitary operations, then you want to get back to the original state, the accepting state, and you do that essentially the unitary operation you see. Everybody, I guess, knows for qubits, if you do a kind of a cycle around the block sphere, you get this kind of sine curve behavior. That means if you read 5 strings, you will get an acceptance of 100%, meaning good. But in between, you have errors, because in between, you also sometimes, when you rotate your state and you project always on the beginning or final state, you always get errors. And it's accepted in this community that if you have less than 25 or less than 30% errors, then the automaton is good. So it's a good automaton, meaning for qubits, for mod 5, it would not be good. The good thing is, we not just have to restrict ourselves to qubits. And I will show you in a second what's the advantage then. So, but let me first explain you what is our qubit. So as I mentioned, we have these spatial modes. Now we use essentially a superposition. So if this is our block sphere and we have OEM +1 and -1 on top and bottom, or north and south pole, our qubit is actually, or a starting qubit is actually on the equator. And now we want to go essentially with our automaton around the equator. And you see, if you go around the equator, you calculate how the mode looks like. It's just a physical rotation. So our unitary operation to realize a finite automaton or quantum finite automaton is just a rotation of the mode. And the good thing is, we not just have one mode or 2 modes, but we have multiple. So, and they're all the same, but for higher order modes, smaller rotations are required. So if we have a device that rotates the mode over a certain angle, and if we combine our modes cleverly, we get an advantage. In the experiment, what we actually did, how did we rotate the modes? It's a simple device in optics. It's a dot prism. So you put a dot prism in your setup, and then you rotate the modes. So we used single photons, heralded single photons that we send in a loop. And because we have the exact timing, how long the photons are traveling in this loop, we know how many cycles this photon did. And in every loop, we rotate the photon a little bit, okay, the structure of the photon, I should say. So if we don't put it in, it's, let's say, in the horizontal structure. We put it in, we rotate it by 36 degrees, second, third, fifth, and so on. And after 5 rotations, we are at the original state. So now we would have a device to detect this mod 5 language. And this is what we did in the lab. And you see it follows nicely. This is what I earlier introduced, this sine curve. But we have 66% of errors, meaning that this is not a very good working quantum finite automaton. But as I said earlier, if we combine these higher order modes cleverly, and in this case it was 1 and 3, then the mode looks like this. And we get a pretty steep decrease already after 1 rotation, after 36 degrees of rotation, meaning 1 reading of a symbol of our quantum finite automaton, we get already pretty low errors. And it stays low over the whole like repetitions and gets perfect in the end, or it should be. We got pretty close. So here we have now a finite automaton, quantum finite automaton that detects mod 5 languages with less than 10% errors, and only requires 4 states, where a classical one would require 5. So there's already the quantum advantage visible. And then we went on, so we put our photon 11 times in the loop, and then the efficiency got pretty bad, so we couldn't go much further, but we put it 11 times in the loop, and we used essentially 8 states, 8 different modes of specific superposition of it, and then we got less than 25% errors, and a near perfect working after 11 iterations. So here, a classical one would need 11 states. A quantum finite automaton requires only 8. So if you want to know more about the details, because I guess the time is very, very limited, so it's recently published in Quantum. I invite you to have a look at it or ask questions right after the talk. Okay, good. So the second part of my talk will be on interferences in spatial structures. So I showed you now one specific unitary operation, meaning a rotation, unitary operation around the equator of these specific states that I showed you. But now I want to make it more general. And how do we do that? We developed, or others also essentially worked on this or introduced this concept of multiplane light conversion. And we developed it for the quantum domain further. So what does it mean? In our lab, we allow ourselves, let's say, 3 planes of phase modulation only. And if we do it correct, we can then send any set of input modes and get out any set of output modes. So we have a device that modulates a certain set of input modes into another set of output modes. So in this case, it would be a Hadamard transformation. So +1 gets to plus -1, and -1 gets to +1 -1. How do we figure out what are the right phase modulations to do so? There is a technique which is called wavefront matching. I will not go into the details. You can look that up, and this was done by others, and we used it for our purposes. So if you do the calculation, you simulate it in the computer, essentially, you will find these kind of fancy looking phase modulations. And when you send light through the device, you send the +1 in, it behaves like this and comes out as a superposition +-1. And if you send -1 in, it behaves like this over propagation and comes out as a +1 -1. So you realize effectively a Hadamard transformation. We essentially have along a single beamline, so it's the same phase modulation. We can send in, it's just a single beamline with only then interferometers, but we have a multi-port. We can do any unitary operation on this qubit in that sense, because we just have 2 modes. But we can also do more. We can have a Q-trit, so 3 different inputs mode, a 3-dimensional state space, and perform with only 3 phase modulations any unitary operation. We did an experiment there where we then used the OEM and the radial degree of freedom to even do on a single photon a controlled knot operation, and you see it works quite well. You want to look it up. It was published a couple of 2 years ago now in Optica. So we have a device that performs any unitary operation. We then, of course, went on and just at this experiment, we just showed that it's working, but we wanted to see a proper quantum experiment, 2 photon interferences in such a spatial mode multiport. And what do I mean by 2 photon interferences? I'll very briefly introduce in case you haven't heard about the Hongo-Mandel interference or 2 photon interference. Usually this is done with a beam splitter. You send two photons into a beam splitter, which is also doing a Hadamard transformation, but in the path domain, not for spatial modes. So if you send in two photons from two different input ports, classically you would expect four different output possibilities. Both photons come out in the same output port, either here to the right or up, or they come out in different output ports. But if the two photons are perfectly indistinguishable in any other degree of freedom than the path, because they're in different paths, then you get interference between these two photons, and they always bunch into the same output port. It's very standard and very, very powerful technique that's to make photons interact or interfere. It's used in quantum computation quite a lot. The experimental signature that this works is usually you delay one photon when sending both to the input, and when you scan your delay and you reach the zero delay between, so they actually hit at the beam splitter at the same time, you get a dip that's always called homomandel dip. So if you see the zero, so they never, you measure if they come out in different output ports, I should say. So if you measure that they never come out in different output ports, you know they bunched into the same output. Okay, so for us, with our spatial mode splitter, that means, okay, now we do the same thing, but it's spatial modes. So we send two photons in the same path, but different spatial modes. And due to interference, we expect that they always come out in the same output, in the same spatial mode, never in different spatial modes, just like with the path, but now in spatial mode and along a single beam line. And briefly, how many more minutes do I have? I didn't check really the time.
Well, we'd better move to the end. Yes, 2 more minutes.
Okay, then I briefly jump through this. So the setup, in case you're interested, we use parametric down conversion to generate photon pairs. We use spatial light modulators to shape the photons, bring them on the same beam path, have our multiport, let them bunch into the same mode, and measure that again with spatial light modulators and holographic techniques. Here are the results. You see they bunch quite nicely. We can also measure it, switch the output measurements essentially to see if they actually come out in the same modes, and then we get another dip, but a peak. So it works quite nice. We achieved in this experiment good visibilities. We improved it since then, and we can measure different input bases and output bases, and it works exactly what we expect from theory. We then moved on and did it. I just briefly scanned it for higher orders. So it's not just a two-dimensional unitary, but three-dimensional unitary and two photons in, and it works as the theory expected. So we are quite flexible. You can look it up. And then very last thing, we see two photon interferences, just like what people saw on chips and waveguides. We see it on a single beam line. We then realized that what we get out here, I mean, maybe you even realized it immediately, that this is a noon state, a two-photon noon state. So what we usually have after bunching, we have it in spatial modes. So very briefly, and maybe then you can look up if you're curious, I will just briefly scan what we did. What does it mean for spatial modes? So there's the OEM modes. For OEM spatial modes, this noon states that are known, that are super phase sensitive in normal interferometers. For OEM modes, it means they are super angular displacement or angular rotation sensitive. And we showed that in this work here, that we actually reach super resolved angular measurements. And then one last thing, we also did it for radial modes, and it will be published soon. There it corresponds to an enhancement in the GUI phase, which is a phase anomaly in optics, which is a very fundamental concept. We then essentially brought it to the quantum level and called it the quantum GUI phase. And it has some nice implications. I just point you to this archive because I'm running out of time. But we use these spatial mode noon states to look what are the applications. And here it's also, you get super sensitive longitudinal displacement, not rotation. Okay, so with this, let me come to the end. And most importantly, of course, reference or acknowledge the people. Marcus here did quite a lot as a PhD student of mine. Raphael was involved in the GUI phase experiment, and Steven did who's now a PhD in Vienna. He did the master with us and did the quantum finite automaton. These are the collaborators. In case you're interested in high-dimensional quantum operations, when we did this experiment, we were so into that we developed a little target. Look it up. according to the name, endless fun. It's really fun. You can program a quantum computer, essentially, high-dimensional one. And then finally, as I guess also we heard it many times already, I'm always welcome for good PhD applications, but most importantly right now, soon there will be an university starting project where we need a postdoc with experimental atom physics background because we want to bring these ideas to matter waves. Okay, with this, thanks for your attention and sorry for running out of time. So
thank you, Robert. Thank you very much. It was a very beautiful presentation in the talk. Now, this is open for questions.
Yeah, Konstantin Lukin has asked the question. Possible?
Yes, please.
Yeah, actually 2 questions to each for different parts of your presentation. With the last one, you mentioned the Horn-Kuh-Mandel interference. Can you explain in terms of coherence lengths and delays what it is?
Okay, so it is essentially the coherence length. In that sense, I would say it's the length of the photon. If you think of it as so we have a certain bandwidth and frequency of a photon that we usually, it's depending on our down conversion process, but we usually carve it or cut it by our interference filters, our bandpass filters. In our case, it was 3 nanometer. We can also have a 10 nanometer. And this gives us a certain coherence time or coherence longitudinal length, if you want. And then the two photons have to get to the beam splitter, or in our case, this mode splitter, arrive within this, of course, coherent length or coherence time. And if we overlap them perfectly, then we have perfect interference. If they are just half overlapping, we get half. That's why this dip, when you look at this little graph here, you see that the dip is slowly going down, and that's depending on how our spectrum of the photon looks. But it's not as sensitive as a normal interference. So it's not within wavelength range. The photons are a micrometer long, essentially, tens of micrometers long. And they have to be within this tens of micrometers. So these experiments are in that sense more stable than normal interferometers, single photon interferometers.
This reminds me that in classical physics, we call this spectral interferometry or optical coherence tomography, for instance, application of the same.
Yes, yes.
Okay, great. Thank you. First part, my question is, I like very much your attempt to use the photons, the different state of photons, to implement for qubits, say photonic qubits, as I understood. Maybe I understood.
Yeah.
And what still, it was old idea, then how to implement it. So my question is, which challenges you see or problems that are most challenging on the way of this type of quantum computing or similar devices? Thank you.
So I mean, there's one thing in quantum information in general, I would say, where photons are the only way to go, and we just heard a beautiful talk before mine, is quantum communication. Like over long distances, obviously you need photons. So they are the only candidates. If it's a modulated, very weak laser pulse, I would consider that very similar. So in terms of quantum simulation or computation, I personally, I always thought like, yeah, these superconducting qubits or the ions are because they are like solid systems. They seem to be more promising. But what has been shown with photons and also continuous variable encryption, so we use discrete variables, but in continuous variable description, but what people showed quite recently, like the company Xanadu in Canada, for example, or also Jean-Lai Pan's group in China, is really impressive. So they push it forward. So I would be more careful now and say, like, for quantum computing, it's also very promising. There's companies that get huge amounts of money. So apparently they solved many of the issues that I would say, it's still interesting how you overcome these problems. But apparently people did already show that they can overcome it or have some other ideas for really scaling it up. In our case, just this one specific quantum finite automaton, we found it interesting we have a very simple system. I mean, it was challenging to have all the details in the lab, but we have a very simple system, and our system performed better than at least the IBM quantum computer that you can use online. So our collaborator, Abu Yakiri Mas, I hope I scrutinized the name too much. he did the same thing or similar thing with multiple qubits on this online available quantum computer, and it performs worse. So of course, scaling up, it's a different story, but it was very interesting for us to see that we can even compete at the moment with these systems with our simple devices.
Thank you, Robert. Thanks for the questions. Even though there would be more questions, we'd better continue our program.
So if you want to ask, just drop me an email or write in the chat. I try to answer there. Thank you very much. Thanks, everyone.
Thank you, Robert.